Hello, this is question 5 from the 2009 MAT. It's got a lot of description at the start because I had to cut the bottom part of the question onto another slide. So we'll get onto that in a moment. Given an n by n grid of squares where n is greater than 1, a tour, key term there, is a path drawn within the grid such that along its way the path moves horizontally or vertically, so nothing diagonally, from centre of one square to the centre of an adjacent square. Path starts and finishes in the same square. Path visits the centre of every other square just once. Right, so 3 criteria for a tour. For example, below is a tour drawn on a 6x6 grid of squares which starts and finishes in the top left square. It does indeed. It's gone to every square and we're not moving diagonally. Fine. For parts 1 to 4 of the question, it's assumed that n is even. With the aid of a diagram, show how a tour, which starts and finishes in the top left square, can be drawn in any n by n grid. So how can we show that we're always going to be able to draw a tour in an even-sided square? So we're going to want some kind of inductive diagram then, where we just build up. So let's draw out some grids. So if we've got 2 by 2, we can have a 4 by 4. If we just do a few of them, and then hopefully once we've done the first 3, then we'll see some kind of pattern that we can then describe and maybe test it on a 4 by 4. Well, it's gone a bit wonky. 4 by 4 grid. Well, my lines are pretty ropey drawing them on here, but it's going to be close enough. So what am I doing? I'm doing a 6 on here, aren't I? So 1, 2, 3, and then 4, 5. Right, so that's our first 3 grids. And right, so the first one, well, that's simple enough. We just go round like that. So we want to get some kind of pattern. So let's go from here. We do the same. We go all the way across. We do the same first 3 steps and do that all the way across, all the way down, all the way back across. Then we got to do a little jink to get a, well, what's that, a backward C shape. Then let's try it again then for the next one. We go all the way across, all the way down, all the way across, up, do some jinks. All right, we've got an extra jink. So we've now got a backwards E-shaped shape on there. So every time then, when we go to the next one, we're just going to add an extra tine to this fork, an extra prong, however you want to look at it. So let's go in on this then and do, what's the chances of me drawing all these lines? Well, and just as I'm saying it, get a wonky one. So we want to have 8 here. Now 8 is a bit easier to do because at least I can just keep splitting things. So this is just to make sure everything does actually work. Now, I'm pretty sure it will do. Split that. Horrible lines. But this is the trouble with being on a screen. Right, so that is 8 by 8. So same thing all the way across. Oh dear. All the way down, all the way across. And then we should have 4 jinks. So 1 tong, 1, 2, 3, 4. Yeah, so we can see now we just need a description that refers to these. So we can say, so what's this? N equals not 1. N is 2, 4, 6, 8. That's what we've got for our n's. So every time n is increased, what are we saying? We can extend the path to the right. That's fine. We can extend path to the right as far as we want, as far as required. Then add in an extra, I don't know what we're going to call it, an extra branch maybe. This might be a better way of putting it rather than going on about prongs and tines and things, but prongs will probably be fine. And extend the path to the right as far as required and add another branch to the, they're not really zigzags, but the, I don't really know, weaving section. I don't know, I call it weaving section. You can kind of see what we're getting at on this. So yeah, I think it's clear enough from the picture. We've established a pattern from the picture that we've gone from no tines, no prongs, to 2 prongs, 3 prongs, 4 prongs. I suppose you could call that 1 prong at the start, but it's an obvious pattern of what we're building up there. So that must be what they're getting at with the aid of a diagram. Right, okay, that's the first part of the question. It's already been quite long-winded. Is a tour still possible if the start-finish point is changed to the centre of a different square? Justify your answer. So, right, let's go back and look at these. So, well, it doesn't matter where we start, does it? I mean, by definition, a tour is going through all squares. So it doesn't matter which one we're starting at, because we've got a closed loop. So that's all that matters. So the answer to this is going to be yes, because each tour is a closed loop. Each tour is a closed loop. So yeah, because we're still dealing with even, aren't we? Yeah, because each tour is a closed loop, so we can start anywhere on the path, or route. Let's go route. Oh, okay, that was easier than the first bit. Suppose now that a robot is programmed to move along a tour of an n by n grid. We're still in the even bits, aren't we? Because they said parts 1 to 4. So it's only the last part where we can include odd. Oh, they've actually put that in the last part. The robot understands 2 commands. Command R, which turns the robot clockwise through a right angle. Command F, which moves the robot forward to the center of the next square. The robot has a program, list of commands which it performs in order to complete a tour. Say that in total, command R appears R times and F appears F times. Right, so uppercase, lowercase. Initially, the robot is in the top left square pointing to the right. Assuming the first command is an F, what is the value of little f? Explain why r plus 1 is a multiple of 4. Okay, so let's start with the f's then. So what do we have with f's? So that's the number of times we move forwards. And the number of times we move forwards, so we move forward to go, we do a command, or execute, but I've written do now, a command F to move to a neighboring square. So that's certainly what's happening, because at the moment I'm not too sure where I'm going with this, so I'm writing down facts. We visit each square. Oh, we visit, okay, and it is quite obvious actually. We visit each square once, so we must have f has got to be, therefore f must equal number of squares. Well, it kind of dropped out pretty quickly on this. So f is going to be equal to n squared. Right, that's fine. And what do we have to also explain? Why r plus 1 is a multiple of 4. So we're initially in the top left square pointing to the right. And r plus 1 is a multiple of 4. What was r again? R is turning clockwise through an angle of 90 degrees. Right, so r is, so we start, we've got some grid, we're setting off on a tour. We're starting up here and we're pointing that way. Okay, we go off on a tour, yada, 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 which you know is doing all of this, dum, bum, bum, and then we're jinking around. And then we come back to the final square coming in here. All right, okay, we've got a change in direction. So we need to put that down then. So when we return to starting square, start square, direction is up. is up. So we are 1 R short of doing 300 to be back pointing the way we started, is what I'm trying to get at, i.e. 1 R command short of original direction. So therefore R plus 1, doing one more R command, equals a multiple of 4. Equals a multiple of 4. No, because we're turning 90 degrees each time, so 4 R's equals 4R equals 1 complete turn. Oh no, actually that should be not 4 little r, 4 big R. So if we keep completing turns, then we must have been going through multiples of 4. We do 1 extra R, we get back where we want to be pointing. Right, okay, that was fine as well. Must the results of part 3 still hold if the robot starts and finishes at the center of a different square? Well, no, it certainly won't, because let's go to red here, because we know we've got, what did I draw? So even for a simple tour, this was the simple one that we had for a side 4, wasn't it? So that was n equals 4. So if we start in the top square, so for this example, if we start in top, how much detail do we need? Will it still hold if we start a different, right? So we don't need to go through every single square. We just need to talk about something which is different to the top left. So if we start top left, then starting direction is that way, and finishing direction is that way, upwards. So we start pointing to the right, we finish pointing upwards. If we start in the square to the right of that, so in the second square, then we can say starting direction is that way still, and finish is also in that direction. So therefore, in this case, little r will be a multiple of 4, not r plus 1, because we've gone back to the same starting orientation, multiple of 4. And I think let's just double check on the question. Must the results of part 3 still hold if the robot starts and finishes at the center of a different square? Explain your reasoning. So that is just a big fat no. We don't have to go through any other squares. Like if you started on, I don't know, which square would we want? Like say we started on the top right square, you'd start off pointing downwards. Oh, that would be the same. Have we got one where we're turning left? Yeah, if we started, say, here, then you start pointing to the left and you come in pointing upwards. So that would be an R minus 1. Would be R minus 1. Is that right? No, not R minus 1. That's turning right. Oh, yes, it would be. Yeah, we've gone one past where we want to be. That's right, yeah. No, that's gone anti-clockwise round. Oh my word. Oh, maybe that is still R plus 1. Either way, yeah, how would that be working? If you started going to the right and you going to the left, and you come in pointing upwards, because we can only turn right. So that'd be going right, which means we're one short of where we want to be, which is the same. So actually that isn't different. If you pick any of the ones on the corner, then I think they're all going to be R plus 1s. If they're going to be the ones on the straight, then they're just going to be R's. So, but still, we don't need to consider all of these corners. We only need to say that starting on a corner is different to starting on a straight. So that's what matters on part 4. Right, the last part, we're now allowed to have odds, and it's got that in the question. Show that a tour of an n by n grid is not possible when n is odd. Right, so we need to wonder if that's going to take part of what take consideration of what we just worked out here. So we know that we've got to do n squared moves. That's something that we've worked out. So we've got n squared moves. So that is f moves. That's our f is n squared. And it's odd. So we've got an odd number squared. So therefore we can say that little f is odd. Okay, how's that helping us? What does it help in terms of the changing directions? Changing directions, I'm not sure I don't know what I can do with that, the little r, because we can little r is only relevant if we've completed a tour. And it's saying that we can't complete a tour. So I'm not sure. Then again, it's the same with f. Yeah, so I'm not sure where we're going with that. We need to end back where we started. So let's put that down. Need to return to starting point. Okay. Plus the other thing with r's, the little r, is it's not related to n. That's the other thing which doesn't seem to help. At least f is a function of n. R is not a function of n. It's a function of well, it probably would be a function of n, but we haven't worked out what it is. We're just saying that it's something to do with multiples of 4 or near to being multiples of 4. We've got to return to a starting point. So we start somewhere on a grid, and we're saying with the other one, it doesn't even matter where we start if it's an even number. We start somewhere in the grid, and we need to get back to somewhere on the grid. And we are going to be moving, say we described it in a different way. I'm finding the R thing, the way they're described, I can see why they're doing this for going around in a tour, but you could describe this in a left, right, up, down as this, and just movement. So we're not actually changing angle. You're just saying left, right, up, down. That's what we need on this. And then we're moving around all of the spaces. So let's go with this, see if this helps. Say we have 4 commands: left, right, up, down. Then we know that adding all of those up has got to, so L plus R plus U plus D, so all of our left, right, ups and downs, because they're all moving to an adjacent square, that has got to equal f squared. Not f squared, n squared, f, which is n squared. Okay. What else do we know? We also know that the number of lefts have got to be equal to the number of rights in order to get back to where we started. And the number of ups has got to equal the number of downs in order to get back where we've started. So that means that we've got the n squared is equal to, well, let's replace the L's and the U's, say, 2r plus 2d. So n squared is even, which is our contradiction. Right, okay, so this is a much more helpful way of thinking about it, at least from my point of view on this. Maybe there is something you can do with these r's, these lowercase r's. I can't see it off of this, but just thinking about it in terms of those left, right, ups and downs, that drops out really quite quickly then. Because, yeah, you have to move the same number of rights as left, otherwise you won't get back to your starting point. You have to have the same number of ups as downs, otherwise you won't get back to your starting point. N squared is even, but we've said that n squared is odd if n is odd. So, therefore, n cannot be even. N is even. Right, okay. That was quite a fiddly end. I think that last part was quite difficult. The other ones weren't so bad. I think conceptually, this isn't too difficult a question. Writing out the explanations isn't easy. So I would say that the explanations are quite tough all the way through this, and the last part of the question is quite difficult as well. Obviously, it looks a complete mess having to squeeze it onto this bit of screen here, but you'll be able to lay this out much more neatly if you've actually got more space on a bit of paper.